Welcome back, ELE 112. We're covering Thevenins Theorem in Chapter 20, Section 2. And so let's get going. Back in Chapter 8, we talked about Thevenins Theorem with respect to DC circuits. Good news, nothing's changed. We have to reduce circuits exactly the same way we did in Chapter 8. Thevenins Theorem, as it says right over here, is applied to an AC circuit. It provides a method for reducing circuits to an equivalent form that consists of an AC voltage, here it is, and an impedance, in series impedance. And again, it works really great when you want to, in the next section, you'll be talking about maximum power being delivered. If you want to know what you can plug in here in this black circle to get maximum power, for example, an audio amplifier, then you have to design your circuit to have a Thevenin out there to match the speaker that you're plugging in. And speakers come in 8 ohms, they come in 4 ohms, they come in 2 ohms, they come in 16 and 32 ohms. They probably come in some other values that I'm unaware of, especially if you're talking about audio headsets. So, that being said, let's move through here and look at the equivalent circuit, which we've already seen in Chapter 8. This box is basically telling you that you've got a circuit with a lot of components. And it's telling you that this impedance in green, it's hungry. It's hungry for voltage and current. And it doesn't know that that voltage and current is coming from 1 part or 10 parts or 20 or 30. It needs a voltage at the load, which matches this voltage, and it needs a current in the load. If you meet those 2 requirements, you are a happy load. Now, that doesn't mean you can build this circuit over here in the yellow. It doesn't mean you can build that circuit and it works just like this, because if that was the case, your home stereo, which has thousands of components, if not hundreds, would be obsolete. Some guy would plug in a resistor and a source and the stereo would work, but that's just not true. Okay, what else? Here is the information in your book. You know, if you look at it, it's the same information that was in Chapter 8. The Thevenin equivalent voltage is defined as the open circuit voltage between 2 points in a circuit. So when you remove the load here, you've got a gap. I'm going to tell you what's behind that gap. You've either got a resistor directly in parallel with it, and that's the voltage that you need to find for Thevenin. Or you've got a box, let's go black. You've got a box with a series resistor that comes out, in which case you have to go find something back here. There's usually a resistor or 2 resistors, or a capacitor, or an inductor. After all, we're in the AC chapter, so it may be more than just resistors. This is the same information you had in Chapter 8, isn't it? Except now, we're dealing with an AC circuit. The good news is the technique does not change. In terms of finding Thevenin impedance, Thevenin, right here is all you really need to know. Thevenin's equivalent impedance is the total impedance appearing between 2 terminals. So here's a circuit. Here's a circuit of some size. And I plug in a load. I'm going to plug in a load across these 2 spots. When I take that load out and I put my eyeball right here, and I look in, and the other thing you got to do is you've got to short the power supply. And if it was a current source, you would open the current source, making the circuit easier. You look in and you start compressing from the left side forward. Right where the power supply used to be is a wire. So, in this problem, you would grab these two in parallel, and then they would combine to form a bigger series circuit, and you would have Thevenin. So here's basically a summary of how Thevenin's circuit works. Opening current sources, shorting power supplies, removing loads. When you do Thevenin, you've got to remove the load and you've got to calculate. When you do Thevenin, you've got to short the load, you've got to short the supply, and you have to remove the load in both cases, right? That's a given. You have to remove the load. Okay, so let's take a peek at a few problems. And these can be a little bit challenging for some people. They just don't see exactly what's going on very clearly. But here's an AC circuit with capacitors and inductors, and we want to find the Thevenin equivalent circuit. So we remove the load, and I wish I could just remove the load, kind of like this. That's how you remove the load, and that gives you the drawing on the bottom with the load missing. Okay, and you look into the Thevenin circuit there. You look into the Thevenin circuit, and you see one of those circuits that I warned you about, that you've got two terminals out there, your eyeball is looking in, and you've either got a parallel resistor there or you've got a series resistor, and there's somebody behind that series resistor. Do you see the black circle? There's somebody behind the resistor. Now that's just an inductor, but there could have been two inductors. There could have been a resistor and an inductor in that path. We keep it simple and we usually leave just one component. So R2, which is right here, gets no voltage. It's hanging in the wind, and it's just used essentially like a wire to get the voltage off of X sub L1. So all the electrons float out here, all the positive charge floats out here, and the negative is out here, and you get voltage across that gap that is directly responsible to XL1. So now you know what you're looking for. You need to go find that voltage. So taking this circuit into account and knowing that this resistor isn't in the loop, we have a simple series circuit. Here it is. So one of your best friends in working these Thevenin circuits is Thevenin right here. And you set it up with, here I am labeling everything, that the voltage across the inductor is the Thevenin voltage, and it's the battery, which is 50, and it's the inductor, which is 75 at 90, positive because it's an inductor. And then your ZT, this is a series circuit right here that we're looking at, right? This is a series circuit. So you can just sum these. I did it in polar. You could have done it as 75 minus 75J minus 50J. This is 75J minus 50J. That's what 50 at minus 90 turns out to be, and this is what I got these things reversed. I better rub this off, say it the right way. Okay, let's rephrase that. This is 0 minus J 50, and this is 0 minus plus J 75 for the inductor. Okay, I just chose to do it in polar. I love polar. It's a pain in the butt to enter in your calculator. This whole quantity that you see here would have been a lot easier entering it as minus J50 plus J75 and put a bracket on the outside and be done with it. And that's certainly your option if that's what you want to do. Anyway, after running through this voltage divider, I come out with an interesting answer of 150 at 0 for the voltage on the inductor. You will have some inductors that produce more voltage on the output because of the inductor capacitor situation and the inductor charging current and then discharging it back in along with the 50 volt power supply. Now, second part of this circuit, Z Thevenin is the open load circuit resistance looking in, and we draw a short in here, and once again you see this is in parallel, but now the resistor that was not around for V Thevenin is very important. Don't lose sight of that. And so Z Thevenin is equal to the parallel branch plus the resistor. That wasn't too bad, was it? But it does take a lot of planning and strategy. So here we are calculating this parallel branch here, and then we add it to the 50 over here, and boom, you end up with Z Thevenin of 158.114 at an angle of minus 71.565. Remember, whenever you've got X sub L and X sub C in the same circuit, you can get some strange numbers. If you're at all shaky, check your answer keys and check your Kirchhoff's voltage law and Kirchhoff's current laws to make sure that the inductor isn't over inputting and giving you larger voltages than you're expecting when they really are normal. Here's another circuit. Power supply is way off to the right. We want to just simply find the Thevenin equivalence. There's a small typo there. Put a Z here, and I will put a Z on my paperwork. After all, we are in the AC version of it, and it's called impedance. Okay, so that being said, the order with which you do these is irrelevant. You can do Z Thevenin first if you want. You can do V Thevenin first. I like doing V Thevenin first, so I'm going to grab and remove the load, and that leaves me with this drawing right here. And I'm also going to take the power supply, and it's 5 at 0 degrees. And you're going to notice that this is it's just a series circuit. It's just a series circuit. So our question is, what causes V Thevenin? So V Thevenin was from this little red dot to this little red dot, and what I've got directly in parallel with it is R1, which is 860. That is, this one is directly in parallel with where V Thevenin is. You cannot tell me that this resistor is in parallel with V Thevenin. The power supply is in the way right here. So the only thing that's causing V Thevenin is R1. So that's what we're after. We need to go get R1 as part of the solution to this problem. Okay? All right. So, simple series circuit. I've been pulling out the voltage divider from my pocket, and you could use Ohm's law if you wanted to. You don't have to, but Ohm's law will work for you here too. You're going to have to find RT no matter what. And once you do that, sometimes Ohm's law is easier, you know. So here's my voltage divider, which I then say is equivalent to VR1, which is Vthevenin. And it's the battery times R1 divided by ZT, the ZT that we have not computed yet in this circuit, but it's just a simple series circuit. It's 860 at 0 plus 560 at 90, right? 560 at 90. But if you don't want to do polar, I've went ahead and I've done this problem with rectangular so that you learn to not fear the Reaper. Remember that song, Don't Fear the Reaper by Blue Oyster Cult? Well, they wrote it about people who were doing Thevenin circuits and were afraid to use rectangular coordinates sometimes. So here we are, we're not fearing the Reaper. We're running this calculation and we come up with 4.189 volts at minus 33.070 for Vthevenin. Step back. Look at the problem. Let me ask you a question. Did we really work hard to get this answer? I mean, we had to compute a few things. We had to make a few assessments, but holy smokes, that's pretty short. That's one step and done. Could Thevenin be far away? Well, let's open the load, and here's our circuit. And I think what you'll see is that R1 is in parallel with the gap, which is in parallel with L2. It's definitely in parallel. So we run a parallel calculation, and again, I decided to educate you on using rectangular coordinates down at the bottom because you can. Remember, this coordinate is 860 plus J0. You see, and the J0 goes. And this coordinate is 0 plus J560. And the 0 goes. That's why we don't have the zeros in there. They don't help us. So I run this computation, and then I go, holy smokes. That's my Thevenin. Done. Wow. Can you do that problem? Okay, here's another problem. Holy smokes, it looks like there's two power supplies here. The only thing is they're in series, which means that we can reduce it. There's no reason to run superposition on this problem. There's no components in between that spot in these power supplies, and from the top to the bottom, it's just two power supplies that are sitting in series, but they're phasor power supplies. So we've got to grab them using phasors. We come up with VS1 plus VS2, and there's one power supply now, and the circuit gets simpler because there's one power supply. Okay? Now, notice that this problem is different than all the other problems on the planet that you've probably worked. They tucked a power supply in here with a 30-degree angle. FYI, this is a homework problem, something very, very similar. So I thought I would look at it, and you see it has phase angle on the battery. That's okay. You just ignore it. All you got to do is add them like phasors. You are experts now at adding 10 at 30 plus 15 at 0, and you end up with 24.18 at 11.93 volts. So now you've got one battery feeding two components, and when we go out there to calculate Vthevenin out here, we discover, looking in, that it's one of these resistors that's just kind of sitting there in the wind doing nothing for the voltage. Okay, now that means that the voltage has to be developed by somebody else. Hint, hint. Somebody else that's usually directly in front of the gap. Directly in front of the gap. That, excuse me, that is this resistor. So that's what we want. We want to find the voltage. This is a series circuit, people. This is a series circuit. The circuit's very simple. You need to go find VR2 in the circuit, and all you have to do is load up Ohm's law, or you could use voltage divider, which is what I used over here. And I ran through the calculation and got 12 volts at 11.933 as the voltage across this gap. That's your Thevenin, okay? That's your Thevenin. Again, I want you to look at the top of this problem, okay, and how complicated you thought it probably was. And take a look in the black area. How much computation did we really do? Not much. And when you can't do these problems, some of them are not going to require very much. Here's the continuation of that problem. Looking for Thevenin, we take the original circuit shown in black and we short the voltage source. And we look in. And what we see is 200K, and this 200K in blue, which can float down here and load up so that we have parallel. Now, do you know what Thevenin is? It's 200 in parallel with 200, which is 100, in series with this, and so your Thevenin impedance is R12, which is the parallel combination here, plus the inductor. And there it is. What do you get? Thevenin. Way cool, right? Okay. Tips, okay? Tips. Let me see what I want to talk about here first. Okay, so here's a typical circuit. You're going to remove this load and take it away. That's going to leave a gap at the yellow dots, and you're going to look into the red arrow with your eyeball. Don't forget, when there's a resistor, a capacitor, or an inductor up here for Thevenin, this part does absolutely nothing. So the voltage that you're after for Thevenin is that capacitor voltage right there. That's what you're interested in. When you're computing Thevenin here, Thevenin requires you to put your eyeball out here and look in and compress the battery, and here's a circuit that appears to have a parallel relationship away from where your eyeball is. Once you compress those, that adds, the parallel adds to this in series, and when you do that, it goes back to parallel with this, and finally, everything in black adds in series with R3. I'm just providing a little bit of support here, a little extra, that you have the capacity to work these. This is called a ladder network, and ladder networks are parallel to series, to parallel to series. You see how that works? Okay, let's see if I can get this out of here. Ladder networks are misleading because they're easy to see the series in parallel, and sometimes they can be a booger to solve. So what I was trying to say was that gets consumed in parallel. Then the blue circle picks this up along with the parallel, and they're in series. So you use the series formula. You use the parallel formula here. You use the series formula for the blue. Then you grab the capacitor here on the outside, and you're back to parallel, and then you grab one of the only colors I got left, R3, and you grab everything else that you compressed, and you're back in series. So it's parallel to series, series to parallel, parallel to series. This is what ladder networks do. Good luck with your Thevenizing.